How's it going, folks? Welcome to Algebra 2. Today we're going to be looking at 8-3, rational functions and their graphs. Today our objective is to graph rational functions. Let's go ahead and get started. So in the previous section we looked at reciprocal functions. Today we're going to look at rational functions. A rational function is a function you can write in the form f of x is equal to p of x over q of x. Essentially it just means that there's a polynomial in both the numerator and denominator. Okay, we can think of these as being x over x plus 2. It can be x to the fourth minus 2x plus 1 all over x cubed minus 2. Okay, it's whatever you want it to be as long as there is a function on top and a function on the bottom, and they are being divided. So rational functions can look very different depending on what pieces they have. Okay, each of the three following are considered rational functions, even though all three of them look very different. For our first one, we have x squared over x squared minus 1. Notice how we have just a horizontal asymptote here, and it kind of makes like a bird-looking design. For our one right here, we have a straight line, but we are missing a piece, so we have a hole. And then our third one, we have 2x plus 1 over x minus 2. We have a vertical asymptote as well as a horizontal one. Okay, let's go ahead and talk about these. So though these functions all look different, they all share one thing in common. They have discontinuities. There are two kinds of discontinuities. The first is a removable discontinuity, one that we call a hole. Imagine that we just pick this point out and put it somewhere else. Okay, and that goes with this function here, x plus 3 times x plus 2 over x plus 2, or a non-removable discontinuity. Okay, non-removable discontinuity is one that has a asymptote, one that doesn't connect ever. Okay, for example, we have 2x plus 1 over x minus 2. So when we're working with a removable discontinuity, this is known as a hole, whenever something can be factored out of the numerator and denominator. Okay, so from our original function, we can see that x equals 2 cannot exist because it will make the denominator 0. So at x equals 2, because it would make the denominator 0, it cannot exist. From there, we're going to factor out the x minus 2 from both the numerator and the denominator. As we can see, the only thing we have left is x plus 1. So we're going to graph the line x plus 1, so y equals x plus 1. But at x equals 2, since it cannot exist from this first statement, we're going to include a hole. So we know we have a y-intercept of 1, we have a slope of 1, so it's going to go something like this. And we're going to continue graphing this line, and then we're going to continue it this way. Now at x equals 2, we know that this cannot exist, so we're going to continue this function until we get to 2. And right at 2, we're going to put a nice little hole there. And from there, we're going to go ahead and continue our function. So we have a rational function here where we have a hole at x equals 2. We know that because the denominator cannot be 0, and at x equals 2, the denominator is 0. And then the remaining function is just the line y is equal to x plus 1. So we're going to have something called a non-removable discontinuity, otherwise known as an asymptote, for every value of x that makes the denominator 0. So from the function, we can see that x equals 2 cannot exist because it will make the denominator 0. Okay, so similar to the last example, x minus 2 is in the denominator, so we can see that x equals 2 will not work. Okay, in this case, though, the numerator cannot be factored, so we're not able to factor out anything from both the numerator and denominator. Since we're not able to cancel anything out from both the top and the bottom, we know we're going to have a vertical asymptote, and that vertical asymptote is going to be the line x equals 2. Okay, so that's what we're going to get with this non-removable discontinuity. In this case, we're going to end up having a function that looks something like this, where we're going to have a value that comes down here, and it's going to approach that asymptote, and then we're going to have something that goes towards that direction and curls up this way. Okay, so this is going to be what this rational function will look like. The most important part, though, and what I'm trying to get at here, is that there will be a non-removable discontinuity. There will be an asymptote at the line x is equal to 2. So let's go ahead and look at one last piece of rational functions. Rational functions will have something called a horizontal asymptote. There are three different cases for when a rational function will have a horizontal asymptote, and they're all dependent upon the degree of the functions. As a reminder, the degree is the highest exponent that a function has. So if the degree of the numerator is greater than the degree of the denominator, there will not be a horizontal asymptote. In this case, the degree of the numerator is 2, the degree of the denominator is 1, 2 is greater than 1, therefore we will not have a horizontal asymptote. In the second case, if the degree of the numerator is less than the degree of the denominator, there will be a horizontal asymptote at the line y is equal to 0. As we can see, the degree of the numerator is 1, the degree of the denominator is 2. Since the numerator is less than the denominator, we're going to have a horizontal asymptote at the line y is equal to 0. Now the last case is if the degree of the numerator is the same as the degree of the denominator. There will be a horizontal asymptote at the ratio of their coefficients. So as we can see, the degree of the numerator is 2 in the numerator. The degree of the denominator is also 2. Since the degrees are both 2, we're going to look at the coefficients attached to both of those. So we can see we have a 2 and we have a 3. So our asymptote will be at the line 2 over 3. Let's look at a few examples. So we're going to graph the two functions given. In our first one, we have x minus 2 times x plus 2 in the numerator. In the denominator, we have 3x minus 6. Now, the first thing we always want to do is factor everything. Okay, everything that we can, we want to factor. So in our top, we have x minus 2 times x plus 2. In the denominator, I have 3 times x minus 2. Now, from this point here, we can see that x does not exist, dne, at x equals 2. Okay, so we know that there's either going to be an asymptote or a hole at this value. We're going to determine that is a hole because we're able to factor out the rest of this. Okay, so from here, I'm able to simplify my expression or my function to be x plus 2 over 3. Okay, so since I have a hole, okay, since I was able to factor it out, I know there's going to be a hole at x equals 2. We're now going to be able to graph this function. This function here can also be rewritten to be x over 3 or 1/3 x plus 2 over 3. We're going to have a y-intercept of 2/3, and our slope will be up 1 to the right 3, up 1 to the right 3, and so on, going in the reverse direction as well. Okay, so our function will look something along this line, but again, we have to remind ourselves that there's a hole at x equals 2. So I'm going to go ahead and connect these, but at 2, I'm going to show a little gap there. And I'm going to draw a nice looking hole to show that there is actually not a value that exists at that location. So we'll end up with a function that looks something like this. Now for the next one, we can see that the value of x that makes the denominator 0 will be 4. So x does not exist at x equals 4. And on the numerator, I see that I cannot factor anything out. So there will be a asymptote at x equals 4. So let's go ahead and graph that asymptote. Okay, that's our vertical asymptote. Now we also need to check for horizontal asymptotes. We're going to look at the degree of both the numerator and the denominator. The degree of the numerator in this case is 1. The degree of the denominator in this case is also 1. Since the degrees are the same, we're going to look for their coefficients. Now the number attached to this is 1, and the number attached to this one is also 1. So we're going to see that there is a asymptote, a horizontal one, at the line y is equal to 1 over 1, which is just 1. So we're going to get a horizontal asymptote at this location here. Okay, the line y is equal to 1. And when we graph this, you can use a table, but we're going to see that our graph is going to do something like this, where we're approaching both of these asymptotes but never crossing them, and the other one, or the other side, will go towards this, where again we are approaching these asymptotes, but we will never actually cross them. And that's all I have for today, folks. Thank you very much.